Hi, my name is Asan Zamir, and my research project is photoluminescence imaging of solar cells. So, why did I choose to do solar cells? I chose solar cells because solar cells are becoming increasingly important to create a renewable economy, as they are the leading cheapest renewable energy source. But solar energy only accounts for 3.9% of the total energy created, while fossil fuels make up 60%. That is a staggering difference. So, to make solar cells more widespread and commercially available, there needs to be more research done. So what is photoluminescence imaging? Photoluminescence imaging, or PL imaging for short, is the imaging of the light emissions that come off a solar cell when it's converting sunlight into electricity. So this will be an image, and indirectly we can tell how efficient or inefficient the cell is by how bright or dark this image, which you'll see later. So what is the main problem here? The main problem is our understanding of solar cell grain structures, understanding of those techniques on solar cell grain structures, and overall better consistency from batch to batch. So solar cells need to be examined at a microscopic level to see how small-scale effects on the grain structure affect efficiency. So there can be defects, just scratches from it being created and stuff like that. Degradation from exposure to air, that's large in perovskites, they degrade very quickly. And it just varies from cell to cell, but examining that at a microscopic level will allow us to infer how efficient areas of the cell are. And then our understanding of techniques can be furthered. So we can examine something like doping, which involves just putting chemicals on a solar cell after it's created. And we can see exactly how these make it more efficient or limit it. And this is actually very important because sometimes solar cells can become more efficient, but their maximum potential decreases from the chemical used. Overall, we need to increase better consistency. So mapping how efficient cells are with PL imaging on a smaller level, we can use that to scale it up and create a more consistent batch to batch, because we can use defects and issues found with the first batch of cells and then try to fix them from generation to generation of cells. So what is my research question? Is it possible to obtain photoluminescence images of solar cells at high magnification and high resolution while replicating realistic operating conditions? So, for photoluminescence, obviously it's just images, and then we want high magnification so that we can see into the cell's grain structure, and then we want high resolution so that we can see what we want to see, and see in fine detail and examine it. So for high magnification, it would be around anywhere from 50 to 150x. High resolution, our camera is a little bit over 4K, so that's what we see. And then for realistic operating conditions, we use a solar cell simulator to simulate the sun's wavelengths to ensure that our cell is basically no different from a cell in its actual operating conditions, which is outside in the sun. Our method involves the development of an ERE system. ERE stands for External Radiative Efficiency, and preparation and capturing data. So we had to build a fully light-sealed box, a non-reflective box, which you can see here, and we had to attach a solar simulator to a stand to observe PL imaging, and then we had to attach the camera to actually take those pictures. So here's the camera, and it's attached to the interface of the microscope, and then we have a solar simulator right here attached at a 35-degree angle to this clamp right here, which is attached to the stand. And then for our box, you can see that it's sealed with this black aluminum foil, and it's sealed at the edges with non-reflective tape. So it creates a fully light sealed box, and it's non-reflective on the inside. So no light coming from here is bouncing around skewing any data, and no light is coming inside skewing any data. So for preparation, we had to prepare by cleaning the cell to make sure that nothing was in the way of the glass layer so we could observe it. And then we had to focus on the cell, which takes a minute, because there's, right here we adjust this up and down to focus on the cell, and so we can get a clear image. And then we had to position the camera using these knobs to position this, and this shows us what we see on the with the camera. So then, when it comes to capturing data, as you can see, we have many wires coming out of the box here. These all go to a laptop, and that laptop is used to adjust the power of the solar simulator and adjust the exposure time of the camera. So we use this to take images at varying intensities, and these varying intensities allow us to simulate solar cells in realistic wavelengths, essentially. So we can get PL from that, and that's how we capture it. So these are our results, and we concluded that it's very much possible to obtain photoluminescence images. As you can see here, there's 4 pictures, and these are just a few of the good ones. There are many pictures we have taken, and you can see here there are very bright white centers to all these pictures, and these are where we believe the grain structures start out from in the development process or the creation process, and then they expand out and become larger, wider dots, and then that's the grain structures we're seeing. These are the actual parts that are converting electricity to sunlight. So it is very much possible, and we've done it. And then results continued here. You can see this is one of the images from before, and we actually went a step further, and we made an implied voltage graph. So implied voltage means just the theoretical limit of the voltage. So this is what we think would likely be the voltage if we were to actually put this cell into some sort of load on it and try to get electricity from it. So right around here, this red area is the highest voltage area, where it is 1200 millivolts, and then this area over here, as we can see, is very lacking. It's around 1150 millivolts. So, but we actually took it a step further. So it is very much possible to get photoluminescent images at high resolution. This is 6K by 4K pixels, and then this is at 75x. So yeah, it's very much possible. And then so for our limitations, we had 3 main limitations. Was creation of the box, illumination, and then PL light observation. So we had to create the box. The box took around 3 to 4 weeks to build. We had to cut all these boards custom made. They are hardboard panels of wood. And then we had to ensure that they were completely sealed, which took a lengthy amount of time because we had to test with light and make sure that nothing was getting in. And then to ensure that this solar cell was actually being illuminated correctly with realistic wavelengths, we had to attach a solar cell here. Our original idea was here, but after much effort, we found out that there is a mirror here that actually negates all of the light that comes in here and makes it all one single wavelength coming back up. So it is not theoretical to use this part. So we have to do it from outside the microscope, which is the best solution we could find was to do it here. And 35-degree angle, we could see the solar cell was completely lit, and no matter what objective we used, we were able to fully light the solar cell. Then to ensure that it was PL light only, we had to cut out all 725 nanometer and above wavelengths by using filters here and setting the power to it in 0 on the Solar Simulator app. And to ensure that everything we got was only PL, we used 725 nanometer and below wavelengths filters here, 2 of them stacked, to ensure that everything we got here was 725 nanometers, and we cut off all 725 nanometers to ensure that all that light was actually being produced by the cell and not just reflecting in and then out to the cell. So for some future applications, there's a loss analysis and the IV curve. So a loss analysis will compare the difference between the implied voltage, which can be found from PL imaging, to the actual voltages we collect if the cell was in a circuit telling us how it performs. So to do this, we would first start the first step here, which is where we're going to continue off if we continue researching. We got our implied voltages, which is what our theoretical voltage is, what we think would happen, and then we will actually put a real load on the solar cell and connect it to some sort of load and observe how much voltage is coming out. So then we would see the difference between this, and how big that difference tells us how much electricity is being lost theoretically. So then we can also do an IV curve. An IV curve can help us understand more about the efficiency of the cell at certain operating voltages, and will let us find the exact point where, this is covered up, it reaches maximum power. So an IV curve will look something like this, and it'll go like that, and we will map it so that every single voltage is the x-axis, every single millivolt, and then on the y-axis, right here, it'll be how much current we're getting. So that is I, and we'll see that as voltage goes up, the current we're getting is getting pretty high. So we want to find the point where this is most efficient, i.e. we're using as little voltage as possible from the cell, but we're getting its maximum current. So that will give us our maximum efficiency of the cell in operating conditions. So that is it. Thank you for watching my presentation, and yeah, thank you.